In this video, we're going to be taking a look at circular motion, what causes it, how to illustrate it, and how to describe it. This video is in preparation for being able to do some math with it. First of all, acceleration is the rate of change in velocity. This is the definition that we had for acceleration when we first covered it in the acceleration video. One of the biggest misconceptions about acceleration is that it just involves changes in speed. The first thing that comes to mind when we hear the word accelerate is speed up. But as we learned in the acceleration video, it can also mean slowing down. And while these changes in speed are important examples of acceleration, they don't give us the entire big picture. To understand that, we have to look at what velocity is. Velocity is both the speed and the direction of an object. So when we talk about speeding up and slowing down, we are only looking at the first half of the definition. What we're completely ignoring is the directional component. Direction is important because velocity is a vector quantity. The direction is just as important as the speed. So just like any change in speed, i.e. speeding up or slowing down, causes acceleration, any change in direction is going to change our velocity and therefore change the acceleration of the object or accelerate the object. This type of acceleration where we change the direction is called centripetal acceleration. Centripetal acceleration is acceleration that causes an object to follow a curved or circular path. Newton's second law tells us for that acceleration to happen, there has to be a force applied to the object. Newton's second law says that when a net force is applied to an object, it will accelerate in the direction of that net force. So there has to be some force causing the centripetal acceleration. We call the force that causes centripetal acceleration centripetal force. Centripetal force is a push or a pull towards the center of a curve. It always acts towards the center of the curved or circular path. This centripetal force is what causes the object to turn, what causes the object to go in a circle or undergo centripetal acceleration. One of the things you'll have to be able to do is draw centripetal force on a diagram. You'd have an object moving in a circular path, and your job would be to draw in this centripetal force arrow. And what I want to point out to you is that it always points towards the center of the circle or the curve. So my object, this blue box, is following the black line going in a circle. The centripetal force always points towards the center of the circle, no matter where the object is. This dashed line represents the direction that the object is moving in. So while the object is over here, it is moving upward. When it is at the top of the circle, it is moving directly to the left. Another way that you can think about the centripetal force arrow is that it's always perpendicular to the direction that the object is moving in. So centripetal force always points towards the center of the circle. It's always perpendicular to the direction of the object's motion. Another thing we need to learn to describe and use is the tangential velocity of the object. The velocity of an object that is going through circular motion is called the tangential velocity. And the reason is it's the same in the drawing as that directional arrow. And that directional arrow is drawn tangent to the circle. Again, another way to think about it is 90 degrees or perpendicular to the centripetal force. Again, this shows us the direction that the object is traveling as well as the speed it's traveling in at that exact moment in time. So when my object is over here on the right side of the circle, that tangential velocity is either going to be pointing straight up or straight down, depending on whether it's going clockwise or counterclockwise. Clockwise, counterclockwise can be used to determine if these velocities are positive or negative. Generally speaking, counterclockwise is going to be a positive velocity, and that has to do with the angle and how the angles are changing. Clockwise velocities are considered negative. So this arrow is pointing counterclockwise. So this would be a positive velocity. Down here, if it's pointing downward, that would be indicating a clockwise rotation. That would be a negative velocity. The magnitude or length of that vector may remain constant as the object moves around the circle. The length of that arrow represents the speed of the object. So what I'm saying here is as this object rotates around the center, its speed may remain constant. But because that arrow is always going to point in a different direction, that object is accelerating. So even if the speed is constant, there is still acceleration taking place. Again, when it's over here on the right side of the circle, that arrow points up. When it reaches the top of the circle, that arrow points directly to the left. If the object were over here, that arrow would point directly down. If that object were on the bottom, it points to the right. The direction of that arrow is going to constantly change, and because that direction is continually changing, we have to say that object is accelerating. Again, even if the speed is constant. Again, Newton's second law tells us that the object accelerates in the direction of the net force. So if you were asked to draw the centripetal acceleration into the illustration, it's going to point in the same direction as the centripetal force. Centripetal force always points towards the center of the circle. That means the centripetal acceleration always points to the center of the circle. So in this position at the top, my object is being accelerated downward towards the center of the circle. If my object were over here on the right, the arrow that we would draw in for the centripetal acceleration would be to the left. Again, always towards the center of the circle. Centripetal force and centripetal acceleration always point towards the center of the circle. The only thing that doesn't is the tangential velocity. It is tangent to the circle, and again, always perpendicular to the centripetal force and now the centripetal acceleration. To quantify this, where we're going with this, being able to calculate tangential velocities, being able to calculate centripetal forces, being able to calculate centripetal accelerations, we must know how to describe the circular motion. Just like we did with linear motion, we had to learn what distance was, we had to learn what displacement is. We have to do the same kind of thing here. We have to learn what distances and displacements are in our circular motion. This is going to revolve around terms like revolutions, radians, degrees, and arc lengths. One complete circle is called a revolution. So when an object has completed an entire circle, we say it's undergone one revolution. This is simply a count of how many circles our object has completed. So when I say 3.2 revolutions, that means we've gone around once, we've gone around twice, we've gone around 3 times, and then we finished another 2/10 of a circle. So it's 3 completes in 1 2/10 of a circle. It's telling us how many circles we've done. That's what revolution means. And the term that we use is revolution, not rotation. Degrees and radians are another way to describe the number of revolutions, how many circles we've completed, but using angles instead. One complete revolution is equal to 360 degrees. We want to do it in degrees, or 2 pi, or 6.28 radians. Pi is an irrational number, goes on forever, at least as far as we know. So going to 2 numbers after the decimal point, hundredths place, is perfectly adequate for the calculations that we're going to do. So 2 times pi, 2 times 3.14 would be 6.28 radians. If you want to find the number of degrees given the number of revolutions, multiply the number of revolutions by 360. So if I want to take those 3.2 revolutions and turn it in degrees, I just do 3.2 revolutions times 360. It'd be 1,152 degrees. Degrees tend to produce relatively large numbers, particularly when the object is undergoing several revolutions. So you don't see them used quite as often in physics, especially upper level physics, as you do radians. Radians will produce a much smaller number because all we're going to do is take the number of revolutions times 2 pi, or 6.28. So instead of multiplying by 360, we multiply by 6.28. Gives us a much smaller, more manageable number. So oftentimes you do see radians used more often in higher level physics classes than you do degrees. And again, it does keep the numbers smaller and a little tidier and easier to work with. This is really dimensional analysis. It's based on the equivalences. 1 revolution equals 360 degrees and 1 revolution equals 2 pi radians. And it is all for the result of unit cancellation. It's 1 revolution equals 360 degrees. So what we're really doing here is taking our given measurement, our 3.2 revolutions, times 360 degrees over 1 revolution, setting up that equivalence as a fraction that will cancel out the given unit, giving us the unit that we want, the degrees. And again, it's the same story here. What we're really doing is we're multiplying by 2 pi radians over 1 revolution. We're just taking the equivalence we're given, this one here, and we're setting it up as a fraction so the revolutions can cancel out. Same kind of dimensional analysis you use in any other kind of conversion. That, of course, does mean we can convert the other way around. If we know the number of radians, we can figure out how many revolutions that is by just doing the opposite operation. So instead of multiplying by 2 pi radians, we end up dividing by it. So if we had a measurement of 4.7 radians and we needed to convert that into revolutions, again, we start with the number we're given, the 4.7 radians. We set up that equivalence, 1 revolution equals 2 pi radians. This time, so the radians will cancel out. So the 2 pi ends up on the bottom. Ignoring the 1 because it doesn't do anything mathematically. The 2 pi is on the bottom, so we divide by it. 4.7 divided by 2 pi, or 6.28, is 0.75 revolutions. So it went around 3/4 of a circle. Again, using the operation, if we wanted to go its opposite, instead of going from multiplying to go from revolutions to radians, we divide to go from radians back to revolutions. We can convert between degrees and radians by combining these two equivalences together. Just a little bit of logic. If 1 revolution equals 2 pi radians, that means 360 degrees must also equal 2 pi radians. Again, if 1 revolution equals 360 degrees and 1 revolution equals 2 pi radians, then these two things must also be equal. If A equals B and B equals C, A must equal C kind of logic. And then using this equivalence, we can convert between degrees and radians. So in this case, I've shown my object going 132 degrees. Again, centripetal force always points to the center of the circle. The tangential velocity is always an arrow drawn tangent to the circle or perpendicular to the centripetal force. If I wanted to put my centripetal acceleration on here, it would just be the same arrow as the centripetal force, again, pointing towards the center of the circle. My object started here and it moved over here. This angle being 132 degrees. If I wanted to convert that into radians, again, my equivalence is 360 degrees equals 2 pi radians. Because I'm starting with degrees, I would put the 360 degrees on the bottom so that those can cancel out. I am going to have to multiply and divide this time because I don't have a 1 in here. There's nothing I can ignore. So I do 132 times 2 pi, or 6.28. I always hit equal sign because I don't trust calculators to do the orders of operation correctly. So I do 132 times 2 pi equals divided by 360, and I would get 0.73 radians. Obviously, if I wanted to go from radians into degrees, I would have to set this equivalence up the other way around. Again, in this drawing, this angle here, between my starting position and my ending position, the object followed the circle all the way around to here. This angle is 3.7 radians. If I wanted to convert that in degrees, I would have to set that equivalence up the other way around. Again, the equivalence is 360 degrees equals 2 pi radians. I've got to put the radians on the bottom this time to get those radians to cancel out. And again, there's no 1, so I have to both multiply and divide. Multiply by the number on top, divide by the number on the bottom. So 3.7 times 360 equals, divided by 2 pi, or 6.28, would give us 212 degrees. This is a 212 degree angle. Again, note the centripetal force points towards the center of the circle. If I wanted to put my centripetal acceleration on here, it would be the same thing. The velocity is a tangent line, or a line that is drawn perpendicular to the centripetal force line. It shows us the direction that object would be traveling at that instant, and which direction it would go if that centripetal force were suddenly cut. We'll be using radius. Radius is the distance from the center of rotation to the object that's in motion. I mention this because sometimes when you look at problems that involve circular motion, they talk about the diameter of the object. They talk about the diameter of the merry-go. They talk about the diameter of the carousel. They talk about some kind of diameter. But you do need to use radius, and it would be half that. It is from the center of rotation to the actual object in motion. In true circular motion, the radius is always constant. The radius does not change. The distance the object travels as it moves in a circle is called arc length. And it's the actual distance that the object goes. Again, remember, distance and displacement are two different things. Distance tells us what the object itself did, and the object followed this red circular path. That red circular path, as it moved from here to here, is called the arc length, and it is abbreviated S. Angle is more like a displacement. It tells us how far from the starting position it's gone, and it measures that in an angular way. So degrees, revolutions, radians, those are more of your displacements in circular motion. Your distance that the object traveled is this portion of the circle that it covered. That is called arc length, and it is abbreviated S. The arc length is related to how far away from the center of rotation the object is. It is related to the angle that it's going to sweep through and how far away from the center or the radius of that object. If I increase the angle, I increase the arc length. So what I did here is I moved this object further around the circle counterclockwise. I increased my angle. And as I increased my angle, my arc length also increased. So increasing the angle that the object moves through will increase your arc length. Decreasing the angle will decrease your arc length. So I moved through a smaller angle. I reduced the angle from the original one. Here's what the original looked like. I took this and moved it clockwise to give myself a smaller angle. That smaller angle did result in a smaller arc length. So the larger the angle that you sweep through, the larger the arc length is going to be. The smaller the angle that you sweep through, the smaller the arc length is going to be. But it is also based on radius. It is also dependent on radius. Given the same angle, given the same displacement, the arc length, or the distance that the object is going to travel, will change depending on how far from the center of rotation it is. The further out and away from the center of rotation the object is, the longer the arc length. The closer to the center of rotation, the smaller the arc length. And it really comes down to drawing that circle and how big the circumference of that circle is. As we move further away from the center of rotation, as our radius increases, the circumference of our circle increases. So we will cover a greater distance, a greater arc length for every degree or radian that we travel. By moving closer to the center of rotation, what we're doing is we're decreasing the circumference of that circle. By decreasing the radius, we're going to make the circumference smaller. So every degree or radian we sweep through will be a shorter distance that we're covering. Again, we're going to take all these ideas and we're going to put them together mathematically to be able to do things like calculate the tangential velocity, calculate the angular velocity, calculate the acceleration, calculate the centripetal force of our object.